So yeah, we started off talking about, or we ended off talking about reactions of alkenes and alkynes, and therefore we're talking about the presence of a double or a triple bond. And we already know that an alkene and an alkyne, they're considered unsaturated, and that's because that double bond can essentially be broken, and you can then attach two more H's to make it become saturated. And so the presence of the double and the triple bond increase the reactivity of that particular hydrocarbon, all right? Alkanes, when we talked about substitution reactions, we said they were slow. One of the reasons they're slow is there is no distinguishing group of atoms. We call it the functional group. An alkane is all single bonds. It's actually the only organic compound that is without a functional group. That's what defines it, all right? So when you try to react something with it, there's really no distinguishing place for a reaction to happen. As soon as you have double bonds and triple bonds, and tomorrow we'll get into where we've added some oxygen into the organic molecule, as soon as you have those types of things, you have electron configurations. I don't know if that's the right term. You've got delta ENs and things that are slightly different than in a regular chain, and so it's a spot where reaction can happen, all right? Especially if you have oxygen in the chain. If you've got oxygen in the chain, you now got this really polar spot, and that kind of attracts reactants to it. For double and triple bonds, with double and triple bonds, it's not necessarily a polarity thing, but it's flat, right? In a regular alkane, there's hydrogens pointing in all directions. They're off on that tetrahedral shape. So if something has to break something, it's got to come in and bump into something. And it's like the hydrogens form this protective area around it, which kind of prevents something from coming in and doing a reaction. But as soon as you have an alkene or an alkyne, alkenes are flat, the double bonds, right? Remember, they're sp2. Alkynes are linear. And so there's these areas of vulnerability where things can run into that pi bond and break it. So that's the functional group is where reaction tends to take place. That's why we call it the functional group. So as soon as you add these double and triple bonds, you're now creating areas of reactivity. Okay. So let's take a look at some addition reactions. Don't necessarily put down examples of addition reactions because you just have a note on addition reactions somewhere. You can just put EG, right? And then number one, halogenation. So defining halogenation here, we're adding Cl2 or Br2. Actually, it could be I2, the example I'm going to give, and I'll put here, I guess, or I2, right? You could have I2 as well. I guess technically you could have F2 as well. I don't know of why that wouldn't be the case. Now, this reaction might look like the reaction we just did for substitution. We started with a Br2 and we removed an H, put on a Br, and then made HBr. But this is quite different. Here, we're going to have a breaking of the double bond. That's going to open up, and I don't need you to write this, but that if we were to break this, that's going to open up kind of like a single electron that's looking for something to bond with. And you'll notice then we've got two sites in which we can put something. You don't have to draw all that. I really don't want you to draw all that, but that's just thinking of what's happening. We're breaking the double bond, and we now have these areas in which something can be attached. And therefore, what we end up getting is CH2 with now just a single bond, CH2, and now we've got our Br, and I know I put it down, and Br, all right? And so we have no other product because both of the Brs added on to that particular bond, all right? So again, I don't need you to draw this, write this down, but essentially we've got like a Br and a Br, and what can happen is when we have the collision, one of the electrons forms a bond there, The other electron forms a bond there. One of these electrons comes down here to make the pair in the bond. One of those electrons ends up down there, and we've got this formation of two single bonds. All right. So again, don't mind that. That's just for kind of clarity. And so yeah, straight up added to it. We better name this just so that we recall how to name it. What we call, well, what's our main chain? What's our main chain? Yep. It's ethane. Yeah, ethane. Very good. Ethane. That's Monday morning, June pause. But that's good. You got it in the end. Ethane. What do I have for branches? Bromo. And how many of them? So it's dibromo. Now the question is, do I need numbers? Can I have two bromos in this molecule but in a different position? Could I not have a second bromo on the first carbon? Could I not have both bromies on the first carbon as opposed to one on the first and one on the second? But that's not what the issue. The issue isn't maybe not that it wouldn't be formed in this, but if I just said to you, draw dibromoethane, you'd ask the question, where do I put the bromines? Do I put them both on the first, or do I put one on the first and one on the second? Right? If I asked you to just draw dibromomethane, I put it on a quiz, you wouldn't be able to complete it without some numbers. So we do need numbers for this. You're right, this is the only product that's possible here. But if I just said draw dibromoethane, you wouldn't be able to draw it without the numbers. So what are the numbers in this case? 1 and 2. So I'm going to have 1, 2 dibromoethane. The question of the numbers is essentially, if you ask somebody to draw it, could they do it unconditionally, you know what I mean, without question, with or without the numbers? That's really what the question is. Okay, so that's an addition reaction of a halogen, which I'm going to do a demonstration of in a moment when we're done these. We can add hydrogen. It's called hydrogenation. And these terms are going to be important. They will be the types of things I will be asking you about, right? So we got halogenation and hydrogenation. Again, this triple bond in here is linear. That means my H2s can come right up the side the double bond. They can flank it, and we can break those bonds. Because this is a triple bond, we're going to add 2 H2s. It's going to happen twice. It's going to happen with the pi bond on one side and the pi bond on the other side. And if we add all of those on there, then I'm going to end up with a CH, right, and a CH. And now I've got my H's up top and my H's down here. And then I still have my CH3. CH3. Now essentially those H's could go written in there. I've kind of expanded it so we can see them where they added. So this is essentially CH3, CH3, CH3. What's the name of this stuff? You've got a name for this? I want a name for this right now. You're right. I'll take that off. What is the name of this when I get rid of this second H? Done. What's the name of that? CH3, CH2, CH3. It's propane. It's just propane. You don't have to call the hydrogens anything special. It's just propane. Propane. So we had some propine. We added 2 hydrogens, and we turned it into propane. Okay? We're simply adding across that pi bond, whether there's 1 or 2. It just determines whether we add 1 molecule or 2 molecules. Okay. Hydrohalogenation. Now, adding a hydrogen halide. I'm going to give you an example of a hydrogen halide. A hydrogen halide is anything that has hydrogen and a halide, like HCl or HBr or HI. Now, it turns out that when we do this maneuver, that there's a question on where to put the hydrogen and where to put the halide. Because now we have the opportunity for two different products, because I'm adding two different atoms. And the way we decide which is going to be the major product is something called Markovnikov's rule. Obviously named after I'm assuming a Russian chemist. I'm going to go out on a limb, say Markovnikov was Russian. And this comes up when you have non-identical atoms being added in an addition reaction. And this is your first encounter, your introduction to many, 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 many little tiny, strange little rules on how reactions happen in organic chemistry. And if you continue on, you'll buy books like this that are filled with these many little rules that you have to memorize in order to complete organic chemistry exams. And along with each of these little rules, there are tiny little explanations on why chemists believe that this is what takes place. And you essentially have to memorize all of these little rules and these little reasons. And it's getting really close to biology memorization. I'm not a fan. But hey, if you like biology and you like memorizing that stuff, this is where organic chemistry is kind of rubbing right up beside that biochemical unit you did in the first unit of your biology class. Yeah, here's one right here. We're going to be talking about this in a moment when we talk about aromatic compounds. Experimental observations of halogenation and nitration reactions of aromatics. Electrophilic aromatic substitution reactions. Depends on whether there's a ring activating substituent or not. I don't know what a ring activating substituent is. If it's ring deactivating, then you get orthoparadirecting. Yeah, this is all kinds of good stuff for you to look forward to. Markovnikov's rule is pretty straightforward. Essentially, if your thing that you're adding has hydrogen and something else, the hydrogen will go on the carbon that has the most hydrogens. So another little saying, the rich get richer. The carbon with the most hydrogens gets the hydrogen. Okay? The reason for it has to do with electronegativities and the access of the halogen, which tends to be highly electronegative, to electrons on the carbon that has less hydrogens, and blah, 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 blah. This course is not expecting you to delve into that stuff that you will be learning when you do take organic chemistry, when you continue on. For us, the rich get richer. The hydrogen goes to the carbon that has the most hydrogens. And it's called Markovnikov's rule. So Markovnikov's rule really only works when you've got hydrogen and something else being added into that double bond or triple bond. Let's take a look at some examples here. So the first example, we're going to add HCl. Again, that double bond's going to break. It's going to open up, leave some single electrons. This bond's going to break. H is going to stick to something. Chlorine's going to stick to something. Which carbon is the hydrogen going to stick to? The CH2, because it has the most hydrogens. That's the rule that we use, Markovnikov's rule. So we end up with CH2, and it gets the H on it, which means it's just a CH3. But I'm going to draw it like that so you can see what's happening. We've got a CH, and it's going to get the chlorine, and then we've got CH3. Now, I'm going to write under here major product. That's not to say that the other product does not get formed. Let's write out what would happen if it went against Markovnikov's rule. Cl, CH with the H, and CH3. This is what we would call the minor product. And throughout this book, actually, I could look up this reaction and I could tell you what the percentages are. But the major product is the one that is formed most predominantly. I don't even think that this is overly major. I think it's something like a 70-30 scenario. 70% the major product, 30% the minor product. And the percentages change depending on what we add. And that's a comment of the fact that, yes, the other collision can happen, but it just isn't as energetically favorable. But it must be really close if we can get something like a 70-30 split. And that's the thing about organic chemistry. If you want to try to make a particular chemical, many of the times you use a reaction that's going to get you the major product, but then you still have to throw away 30% of what you've made because it's not what you want, right? And so that's the way organic chemistry kind of works. You kind of work in percentages and figure out how much you can get, and you try to maximize your product, but there are still things that kind of keep you from getting that actual value. In a moment, if I get some time, I'll look up, I'll see if I can find that percentage. Let's name the major product. What's the main chain in this guy? Again, you got to think of this as being a CH3. So what is this guy? Propane. Propane. And where's my branch? What carbon is it on? So it's a 2-chloral. 2-chloropropane. And what's this one? 1-chloropropane. Okay? So Markovnikov's rule predicts the major product. That's not to say that the other one isn't made. It isn't made in the same amount. And again, 2 of them will be added. And I'm going to have you draw just the major product on this one and name it. And I'm going to look up those percentages for the other one. Because it's a triple bond, and they will add on both pi bonds. And you just use Markovnikov's rule twice. You can do it in 2 steps, but it can be done in one shot when you draw it. Just think about the fact that you're going to add one and then add a second one, right? Yes, it'll add on all the hydrogen or all the pi bonds. It'll add on all the pi bonds. I can't find it. Silliness. We'll keep going. I'll take another look in a minute. So somebody tell me what we're getting, and you don't have to tell me that the H's are sticking up. Tell me if they're CH3s and if they've got branches. Somebody describe to me what you've got. Yep. C and then two BRs. Yep. So you've done Markovnikov's rule twice, right? Put the H on the front each time. And then a CH3, right? And again, this is major. It's a major product. We're not drawing the minor. And what's the name of this thing? 2,2, because each branch needs its own number. And then I need a dibromo propane. Okay? All right? And let's do, I think, just one more version. You can actually also add water across these guys. It's the same as before, except we treat it as a hydrogen with an OH on it. And it's not really a hydroxide. I guess you could think of it like a hydrogen hydroxide, but it isn't, because it doesn't take the negative charge with it. When it falls apart, it's an H with a single electron, and then that O also has a lone electron to stick to it. But you add it the same way. You use Markovnikov's rule. Wow. I could look at all the energetic reasons on why Markovnikov's rule works. I used to know this. Ooh. I don't want to go down that path. Not right now, anyway. Not looking right now. All right. I couldn't find any percentages, but I found a whole lot of explanation on why. Okay. Maybe I'll look at that later. What do we have? Again, don't worry about the individual H sticking up. Just group it as a CH3. Stephanie, what do you got there? CH3. C with an OH on it. Yep. And it's a single H. Yep. CH3. And tomorrow we're going to learn how to name alcohols. This is an alcohol, but we can name this guy as a branch. You can name alcohols as if it's a branch, but we're going to learn tomorrow how to name it as if it's its own functional group. But for today, let's give it a branch name, and we actually call this a hydroxy. It's a hydroxy group. So if I told you that it's a hydroxy, we treat it just like a bromo or a chloro or a methyl or a hydroxy or a phenyl. What's this going to be called? Yeah, 2-hydroxypropane. And again, this is the major product. Okay? And we'll deal with the OHs a little bit later on again as we keep going. Okay. So there are some homework questions, but I'm going to keep going and talk about reactions of aromatics. All right? Actually, what I will do right now, I'm just jump ahead for a second. More examples. Oh, we should do some examples here as well. Do I have that broken into two? Usually that's where I get at the end of a day. Let's write that stuff down. So let's write that down. Oh yeah, we're doing good for time. I'm going to do these examples with you before I show you, and then we'll do reactions of aromatics. Now, I've jumped ahead and I've created some example problems, and I do want to go through these with you. And that's because this is a type of skill that we do need to practice. Just giving you reactants and making you find the products is easy. But there are other ways in which we can ask questions. And if I don't practice this with you, you all crash and burn on the test. So I need to show you of an alternate way in which we ask questions based on this stuff. And that's what this is here in a moment. So I'm going to just advance ahead. And we're going to do these examples together. Write down number 1, just as you can call it more examples. And then we'll do number 1. I'm going to start the Smart Notebook, because I'm going to do this in the Smart Notebook. And so if this blocks your view for a moment, I apologize. I'm hoping I can. That's not bad. It'll get out of the way in a moment. Once it fires up, I'll bring back. So in this first example, it really is straightforward, like what we've been doing, except I don't give you the chemical. I'm making you write the reaction from kind of like a word equation and then get you to determine the products. So don't write them both down. Just write number 1 down. We'll do it together, and then I'll let you write number 2 down. So in the first one, this is the organic equivalent of when we talked about types of reactions back in grade 11, right, where I told you what the reactants were, and I need you to figure out what the products are. So this is just like the examples we did, except we have to draw them up ourselves. If you're done writing, start drawing out 2-methyl-1-butene, all right? Because that's the thing that I need you to be able to do. And it's just like the naming and the drawing of the structures we did in our quiz, except now we've put it into a reaction problem. So we need 2-methyl-1-butene drawn first, and then a plus HBr. Two-methyl-1-butene. I'm just writing it out because I don't have it here. 1-butene. When you draw it, start with the end. We've got a butene. How many carbons? How many? 4. 4. Yep, but. Pent is 5. 4. 1, 2, 3. Oops, that's horrendous. 4. See if I can fix that. Where does the double bond go? Yep. After the first carbon. Where does my methyl go? On the second one, right? CH3. And let's add our H's in. H2, full, H2, H3. So that's the tricky part, drawing it up. Plus HBr. We ask ourselves, okay, where are we going to add across? We're going to add across the double bond here. I've got an H and a Br. I need to use Markovnikov's rule. Somebody tell me the product. Don't tell me where the H is sticking up. Just say H3. What do we get? CH3. Oops, not a plus. You keep going. Yep. H3, C, H3, and Br. Good. CH2, CH3. Excellent. Typically, we ask you to name these. What's the name of this one going to be? Yep, Corey?
2-bromo, 2-methyl butane.
2-bromo dash 2 dash methyl. Excellent. And then what do we say? It's butane? Butane. Okay? All right. That's not too bad. Now the next examples are something that are a little tricky, and this is where, if you're good at this, you have the potential to be a good organic chemist. What we do in the next examples is we tell you the product that we want. We tell you what we want to be formed. And then we ask you to draw the reactants. What could we put together to form that product? And this turns that whole idea on its head. We probably don't do enough of that. I mean, that's probably my fault because I'm the one who's teaching you here. I should maybe make you do that more often in even just regular chemical reactions. This is the product we want. You tell me what I need as a reactant in order to get this. And that becomes a tricky problem. Now you have to really know. You have to think. You have to think about what type of reaction. In this case, you don't have to. It's an addition reaction. I would literally do it in reverse, right? I'd draw the product, and then I'd think back to what had to happen. So we're going to start with an alkene in all of these. So we're starting with just the double bond. They're all addition reactions. We can add all of our examples that we've used. We can add just a halide, Br2, Cl2. We can add hydrogen H2, hydrogen halide, water, to get these different products. Okay, first one, butane. Let's do a clear. Can I clear? Clear? Oh, that's exciting. So the first one is butane. Butane. That's what we want as a product. I would literally draw that over here. I would start by drawing butane. CH3, CH2, CH2, CH3. If I'm creating butane from an alkene, what do I have to add to it? What had to be added to that? Yeah, H2. Because I had to fill it right full of hydrogens. I have 3 possible places for a double bond. Does it matter in order to get that product? Doesn't matter in this case. I could start with 1 butene or 2 butene. You pick one. If I'm only asking for one reactant, 1 butene or 2 butene. CH2, double bond, CH, CH2, CH3. In this case, I picked 1 butene as my reactant. Pretty straightforward. What's my second example product? What do we want here? You're going to make me alt-tab back, or is somebody going to tell me? 2, oh, look at that. I did a dash in there. 2,3-dibromopentane. 2,3-dibromopentane. Again, draw your product up. Pentane. 1, 2, 3, 4, 5. I need a bromine on the 2 and a bromine on the 3. H3, H, H, H2, H3. I'm starting just with the alkane. Sorry, alkene. It can only have carbons, hydrogens, and a double bond in it. What did I have to add to this one in order to result in that product? Yeah, Br2. In this case, the location of the double bond, I think it has to be in one spot, right? It can only be in this area in order for that to be broken. So this one's not too bad either. We have a double bond in the second position. CH3, CH, double bond, CH, CH2, CH3. What's the name of this stuff that we started with? Yeah, 2-pentene. Got to locate that double bond with the number. Okay. Which one is what are we doing? C? Actually, I'm only going to do one more, and then we'll keep going. You can do the other one as an extra practice problem. What is this next one? What are we trying to make here? You didn't write it down? Anybody else write it down? 2-hydroxy, sorry? 3-methyl pentane. And I wrote a pentate. I don't know why. I forgot all kinds of stuff, did I? Pentane and methyl. Okay, let's draw up the product. A pentane, 1, 2, 3, 4, 5. A 2-hydroxy, an OH, a 3-methyl, CH3, and then that's it, pentane. So H3, H, H, H2, H3. What do I have to add to this guy in order for that product to be formed? Water. I have to add an H with an OH. And you can write it like that. I would accept that. You could write H2O as well. Okay. Now, where's my double bond going to go? I have actually two choices here, right? Because it could either have gone here or it could have gone here, right? The second one, let's think it through if it was at the second one. If it's at the second one, right, then this is gone. It's not there yet. My double bond is there. And I'm going to have, 1, 2, 3, 1, 2, 3. I'm going to have, oh, wait a minute, 1, 2, 3. Look at it, I've got a mistake here. See this? Oh, no, I don't. I've got the right number of H's. Okay, so which one did we want it on the second one? Is that what you suggested, or did you suggest the first one? The second one. If I have the second one here, it means I've got an H and an H. And it means that I could get both, right? Because I've got the same number of H's, which means Markovnikov's rule is going to get me both of them in equal amounts, probably. There is no Markovnikov's rule being used here because the H's are the same. If I have it on the first one, then I'm going to have an H and 2 H's, right? And where's the hydrogen going to go on that one? If I have an H on my first one and an H on the second one, yeah. That's going to go on the first one, and my OH will go on the second one, right? So if I put the double bond here, Markovnikov's rule is going to give me a major product that I want. If I put this one here, I'm going to get a 50-50 split. I probably will get some of that product, but Markovnikov's rule would guarantee me to get more of it. So I'm going to put it on after the first one because Markovnikov's rule is going to give me more of that product. So I would put it C with the double bond after that first one, H2, and then this is H, and then CH with the CH3, and then CH2, and CH3. Okay? What's this called? Jason, what do you got? 3-methyl 1-pentene. Okay? So there we have to think back to see which one will Markovnikov will give us the major product. Okay, so I'll leave this last one. It's the same idea. You can do it as a practice problem if you'd like. There are some more practice questions, all kinds of it on that. And at this point, I'm going to just show you this little reaction here for a moment. And as I'm doing that, I'm also going to stop this and give